we have not yet solved? Okay, yes, right. Yes, right. So yes, we had proved that. That's right. We had proved that that problem is same as some earlier problem, right? So I think then that's fine. We don't need to worry about that. Okay, so today, so what should be the next thing? Yeah, let us, while I think of more variations, I am little unprepared today, but this is one which I have thought of earlier, and we should try to do this. Pairs of paths. Okay, pairs of paths. So till now, we have been only looking at one path at a time and number of such paths, right? So like one person is walking from one place to the other, and we are counting how many ways he can go. But if two people are walking, right, and they start from one place and go to the next place, their paths could be different. So that's why we're going to count pairs of paths, or rather number of pairs of paths. Let's think about this. It's not difficult to begin with, but all these problems I'm doing with some plan, because later these will lead to theorems, so that it will evolve into theorems, I should say. I mean, anything you do may evolve into theorems, but these is known for sure, and those theorems are very useful. So here the question is that we want to again start from the origin, and now I will stop drawing the grid. I'll not draw the grid. I'll just tell you the coordinates and just roughly put it on the picture on the screen. So let's say that from 0, 0, we want to go to anything. So we can go to 7, 6. Okay. And we will look at pairs of paths. So first of all, let me tell you the moves. The moves are, as usual, north and east. Okay, these are the moves. With these moves, how many paths are there? So how many paths? Okay, so just quickly answer this, then I'll introduce a pair of path. Sorry. This is the first question we had done in this topic. So this will be easy. So the moves are simple, and we just want to go from the origin. Obviously, how many paths from the origin to 7, 6? So come on, we know this, right? Yeah, 7 plus 6. I lost your voice after that. Yes, so what should it be? That's right. So how many different paths could you get? So 7 plus 6 and what more? It's certainly not 7 plus 6. There are many more paths. Seven plus 6. Yes. So there will be 7 plus 6 steps. Right. So 7 plus 6 total steps. That is correct. And that is important. But here I'm looking for the answer, because we know this one already. But anyways, yeah, 7 plus 6 steps is obviously the first step, or rather 7 plus 6 steps is the first observation for us. So meanwhile, you guys think, I'll just draw the lattice. Yes, right? Yes, that's right. And that is basically 7 plus 6, choose 7, okay? But again, my suggestion is do not just memorize this formula, obviously. Yeah, needless to say, okay? What is the explanation? How would you explain this? Yeah. So this answer is yes. That's right. And then why? So why should it be 13, choose 7? Yes, I mean, you have almost said everything, but still. So we have 13 blank spaces. It's always good to review this because this kind of argument will keep coming in different ways. 13 blank spaces, 7 ends, 7 e's, 6 ends, right? So why, yeah. So why is it 13 choose 6 or 13 choose 7? Or why, basically, that is just a language. Why is it this number? So then why divide? So why should we divide and why should we multiply 7 factorial and 6 factorial? So yeah, so you have to, this explanation is still incomplete though. Okay. Yeah. Why do we need to divide? Or even if you could just explain how does choose pop up here, right? Why is it 7 plus 6 choose? So what Shana said is like a mechanical, it's like an explanation in the sense of, okay, this is how the pieces should be fitting. Okay, so that's kind of explanation. I'm looking for certainly a more precise explanation. Or maybe you can try to also say how the choose suddenly, what is it that we are choosing? Like it seems like an arrangement problem or permutation problem. What are we choosing here? Okay, but this will still not be precise, maybe, but let's think about it. So you guys have to revise a bit. Okay, no problem. I mean, yeah, I suppose these arguments are not completely simple or not trivial. And yeah, the first time you're doing this. I mean, so it is good enough to know the formula for sort of things. And you can also, it's also a formula in your school books, as means in the permutation chapter, right? E's and N's, and you're permuting a word. Basically, you're permuting this word, which has 7. I mean, this is not a word, but mathematically it is this word. And you are just permuting, creating all jumbles of this. And we know that there are 7 things of one kind, 6 things of the other kind. So it should be this. But I'm looking for some sort of an explanation so that if it comes in other disguises, like already this path problem is one disguise and many more you will see. So how do we explain? So see, there are only 2 types of things here. So it's not very difficult in the sense that there are only 2 types of things here, right? So the first key point is two types of things, E and 6. Now ask yourself, if I have to permute these 7 E's and 6 N's, then how can I do that by some sort of a choosing? How can E's and okay, please think about it. Okay, I am not going to say the answer now. This is not difficult, but please think about this. Revise a little bit if you need to. Think about it. I think if you have more time, you can answer this. Okay, but this is fundamental. But since we have the answer, I'm not really, it's not, so it's fine. No, but let's do it. I think we should. No, let's do this once here. Yeah. See, if you want to permute two types of objects, right? So what do you have to do? See, already 13 blank spaces we have isolated, right? We have isolated this concept of 13 blank spaces. See, basically it's that you have to choose, right? So basically the answer is that by just choosing seven of the spaces, 7 of the 13 spaces for the ease, right? Choose 7 out of, and the spaces are in some sense distinct because this is the first space, this is the second space, this is the third space, and so on, right? So choose 7 out of the 13 spaces. And that's why it should be 13, choose 7. Okay. And we know that 13, choose 7 is this. Now, again, that also requires an explanation, right? But fine, let's keep it till here. Okay. So this problem, but what I want you guys to see is that this problem is just from 13 people, you want to choose 7 people. Does everybody see that? How this problem is the same as choosing 7 things from 13 things, choosing 7 people from 13 people, choosing some books from 13 books, just choosing. Does everybody see that? How this problem is the same as that? And then we just applying the choose formula. I'm not asking for an explanation of that. Okay, just see, take your time, no rush, see if this is clear. Okay, so it is clear. Okay. All right. Let's test this in the sense that let's test ourselves if we have understood this. Let me do a problem which has not to do much with lattices, okay? Okay. So choosing and permuting. Yeah. These are somehow connected, we are seeing. Okay. Some kind of permutations where things are of the same type with repetitions. Their permuting reduces to choosing is what we have seen. Let me just do one more problem, see how we tackle it, and then we can see if the concept we just talked about helps or not. So let's say that there are 5 men and 5 women, okay. Or I should just say 5 pairs of, yeah, that's the way I have to say, 5 pairs of, so there is this pair, first pair, second pair, and like this. Okay, so there are five pairs. Now the question is that, so there are 10 people in total, right? So how many ways to seat the 10 people so that for any pair, the, I guess, a woman comes before, or comes or sits to the left, comes before the man. Okay, so you see what I'm saying? There are 10 places. Okay, the 10 places. We want to just seat these 10 things, 10 people, but we want this condition. Okay, so let me let's give an example and ask you if this is correct or not. So we have 1, W2, W3, W4, W5, W1, M2, M3, M4, M5. Is this arrangement legal? Is this? No. Okay. That's perfect. Wait, something is vibrating. 1 second. I do not think it should be so simple. Okay. Yeah, I don't know the answer, but I don't think it will be so simple. So yeah, but at least you understood we understood the question to begin with. So now we can start. Okay, so just take 1 more minute and think. Then we'll see. Then you can tell your answers, and we can then see if they're correct. So on. So the question is clear for everyone, right? Okay. Okay. So now let's see. Yes, yeah, only before. It doesn't have to be just to the next, right? So yeah. So the woman can be here, the man can be here, and then the woman too, and so on. This is okay. So they don't have to be next to each other. Otherwise, it's a very simple question. That's the textbook, your NCRT question. Yeah. It can be in any way, but it's only that suppose for the first this thing, right? This W1 should come before M1. Yeah. So it's not important that W2 comes. Okay. This is okay. It means that for every pair, right? For every pair, I mean. Yes, yeah, that's right. For every pair, the woman comes before the man. So the woman doesn't have to come just before, but she can come at any point. So it could be like this. So you can see this is also, this is legal. All the women you seat first, and then you seat all the men. See? But you say the details, because I mean, considering different cases and solving is a pretty vague. Like, you understand, yeah? What is the method? Yeah, how would you start this problem? Like, what are the cases that we will be considering? I mean, at least few that, yeah, yeah, that we can begin to. W1. Okay. So this is a case, right? This is a case one, maybe, if W1 in the first place. So W1 doesn't have to be in the first place. But if W1 is in the first place, then okay, yes. But then how do we continue this? No, no, no. Think about it. It is not similar for all the pairs. Because it really depends, right? What you're placing where and so on. Suppose you place the W1 and M1. So suppose you place them like this. Now you're going to think about W2 and M2, right? So this case, we are assuming that all empty. Everything was empty and you did this, right? Then only we can say that there are 9 choices for M1, right? Everything was empty. The first woman comes, places in the first place, and then the man has 9 choices. M1 has 9 choices. Yeah, but here we are assuming that everything else was empty. So now next step would be more complicated. No, there are many ways to seed them. We already gave some examples. So it could be, so when you could do like this. This is another example, right? Just like this. And then I had given another example where you place all the women first and then all the men. And you can make many examples. No, that we have to, no, but no, 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 no. So the condition is that, okay, so my condition is that for every pair, so it means that for every pair, in that pair, the man, and not the, I'm not saying men, right? And not the woman, but the woman. So you take a pair, for this pair, W4 should come before M4. Okay. W4 doesn't care about M3. Okay. Otherwise, the answer will be 1. You're right. Otherwise, all the women have to see first and then all the men have to see it. But this is, yeah, only about the pairs. So this seems, so this is a problem in like permuting 10 things, but with some very strange conditions in some sense, right? Some sense there are some strange conditions which we are using. Yeah. If you guys, yes, that's right. Yeah, so that's why it's a very strange condition. Usually the conditions are where, you know, they are next to each other or they are not next to each other. Simple conditions. Those are exercises. But here you have to really look at, well, there are many ways to do this problem. In fact, it's the first time I did it in a unnecessarily complicated way. And then I think I got the idea from some student only long time back. But then it was a very simple and elegant idea. No, no, no. But it really depends how many places are, means, how many men and women you have placed earlier, right? Ah, yes. So that is very similar to what has been said here. Okay. But the problem, see, the problem is here that if you take this case where W1 is in the first place, then there are 9 choices for M1, then it, yeah, let's see. Yeah, yes, yes, yes. But okay, so 10C2, then 8C2, then 6. So why? Why? What does this mean? Like, you're adding them. Okay, so why are you adding them? Okay, 1 minute, 1 minute. So there are 10 seats in which 2 women can sit together. Okay, but why do you want 2 women to sit together? Yes, yes, no. So if women comes before the man, so that has to do with 10 choose 2. But why? But that is not. Ah, no, no. So it is the idea. So this can be used in a sense that what does 10 choose 2 mean here? Think about this problem from different angles. Okay. So one way to think about it is that M1 and W1 walk into the room, right? So M1 and W1 first come into the room. And then someone tells you 10 choose 2. Just someone gives you a hint, let's say 10 choose 2, shouts out 10 choose 2, and that's all. Then what does 10 choose 2 have to do with M1 and W1? Let's forget about the rest. Such that M1 comes before W1. No permutations, and that's why 10 choose 2 is the right thing for that. Okay. So number of ways to place the pair M1 comma W1 is 10 choose 2. It is not 10P2. It is not 10 into 9. Okay. It is not 10 into 9, but because we cannot have W1 M1, we cannot have this. Sorry, we can have this. We cannot have M1 W1 like the other way. So it is, so when M1 and W1 walk into the room, you cannot do this. Okay. What you need to do is you need to place M1 and W1 so that W1 comes before M1. But what does that mean? All it means is that you need to choose two places. Once you choose two places, is there anything else to do? Not really. Yeah. That's all. We need to just choose two places when M1 and W1 walk into the room. So M1 and W1 walk into the room. M1 and W1, of course, this you can think of this in many ways. M1, W1 come into the room. What do we need to do to place them? To seat them happily, I mean, as the rule is, to seat them according to the rule, there are 10 choose two ways. Okay, so this is the way to do this, right? Because so think about if you look back at this, you will realize, this makes sense. So when I was discussing with one more person, so what they were doing is they were first placing all the men or all the women and then trying to do casework. Okay. But if you look at the condition is not really, the condition is difficult when you could say and all that, but what is it? Right? The condition is like the condition of M1 has to do with W1 and not with W2. And similarly, M2 has to do with W2 and not with W3 and not with M3, right? So that's why you have to figure out in what way are you going to place your things. That is the freedom we always have, right? In what order or way, what order I mean, I'm not saying what permutation, I'm saying how do you bring in the guys? How do you bring in the players so that your counting becomes easier, right? In what way will you bring in the players, bring in the actors of this game? This is what you have to think, right? What perspective? So for this problem, you should not be bringing in all the men first or all the women first, something like that, right? You should bring in the pairs because that's how the condition is. Okay, but these things you'll pick up over time as you practice these problems, and also not just practice but observe these things, the way you solve them or the way you do them in the class or the way if you're reading a solution somewhere, you should think about these things, right? Why is it done like this? It's obviously that is not as effective as you actually spending a lot of time, but still it's pretty good. It's a good thing, it's a good thing to do in the sense that yeah, you should think why is this more effective? Like even though you could not come up with it, but you should think maybe that okay, like what little hints could I have given myself or could I have got so that I would have done it, right? And it's really that the condition is like this, okay? That and then the way I said, okay, what next? So 10 choose 2 that Unap said, this does have to do with it. It's at least one, there's one way to do the problem. But what next? So what's the natural thing to do? We have placed M1 W1. So what's the next thing to do? Okay, so basically see if you, so how many, so the question is, how, if I ask you this question, how many ways to place M1 and W1 in 10 places such that W1 is before M1. Let's try to answer this question independently of this. Let's forget about the 10 choose 2 for a minute. So here the problem, so the problem, we have made the problem drastically simpler now. We have removed this. Oh, 1 minute. This is some company, sorry. Yes, yeah, so you have M1 and W1 and you want to place them in 10 places. So there are 10 places for them, but only 2 people. But you want to ensure that W1 comes before M1. How many permutations? Let's just think about this. So forget about all the other people, okay, all of us, and let's just think about this. So it's like 2 people want to 10 seats, but the only condition is that, let's say, the elder one wants to sit to the left, something closer, something like that. So how many ways should be there? What is the n? So can you say it in a simpler way? Some example. M1. Okay. So it's just 3, not 3 factorial. Yeah, 3, 3. Right. That's right. That's right. Yeah. So this is right. I mean, if M1 sits in the second place, so you can just do casework, right? If M1 is in the second, but that's not a good way to do the problem. So if M1 sits in the second place, then there is one way for, sorry, then there is one way for W1. If M1 sits in the second place, if M1, but anyone can think of a better way. M1 sits in the second place. Sorry, if M1 sits in the second place, if M1 sits in the third place, then there are 2 choices for W1. These are all different, right? If M1 sits in the third place, now this is already a different case. Sorry, fourth place. Then there are 3 choices, and so on. You can add up to 9, and this would be 10 choose 2. You can check that. This, but that's fine. I mean, this is not a very interesting. This is okay. This is interesting for some other reasons, the other things which I'll ask. I think I'll just ask it as an exercise from here. That's a good, is the good idea for some very interesting thing. But we want a more direct way to answer. Come on. So permuting two letters, 2 things in 10 places. Right? So okay. Let me ask this question. So if there was no condition, then what the answer would be? Come on. If there was no condition, just no, only 2 people. That we don't have 10 people, only 2 people. So this is not in the question. No, oh, 10 factorial is too big, right? There are only 2 people. How will you get 10 factorial ways? Think about it. No. Why? Okay, this is okay. So we need to do this thing here. Let's do this. This is a fundamental question. So no problem. We need to do that. Okay, so let's do that question. No issues. So let's do that first, then this will be automatically clear. Yeah. So 1 minute. Okay, give me 1 minute. Just take this problem in a simpler place and think. See, if there are 10 people and 10 places, then the number of permutations is 10 factorial. Okay. Now, how do you do this? There are many ways to do this. Either you can think from the people's perspective and place them, or you can ask the places which person you want to seat and so on. Okay. Please write a proof. Okay. Just write one of your own explanations. It's important. Now comes the next one. If there are, let's say, 5 people and 10 places. Now let us just use, so let's not forget about, so there is a formula which formally I have told you guys, but forget about any formula. Just do this. There are 10 places. Five people. How many ways can you seat them? So don't jump to answers like 10 factorial, this factorial. No, just do it. Let's just do it like multiple using just the definition of just multiplication principle. Just do it as if you don't know any formula, but you just algorithmically putting one person at a time and just seeing the number of choices and so on. Let's do this. Sorry. Okay. So now it's only that I have made the number of people smaller and number of places more. So this is a simple variation of permutations. So let's just think about it, right? If the first person walks in, how many choices does he have? Just break the problem into steps. Yeah. So how many choices for P1? Yes, come on. How many choices for P1? 10 choices. Okay. How many choices for P2 after P1 has been placed? Right? For each of those 10 choices, there are 9 choices. Okay. And in this way, if you go, then what will the answer be? 10 into 9 into 8 into 7 into 6. So it won't go till 5, remember, because already 5 numbers are placed. Okay, so this is the formula, right? This is what we get. And this is, you can write it. You can check that you can write it like this. 10 places, 5 people, permuting 5 things and 10 things. And this is also called 10p5. P is used for permutations. Okay, but all those are all those condensed forms of useful, but the fundamental thing is to be able to come up with this. And did I do anything special? No, I'm just taking the people and placing them in the places one by one and asking you guys how many choices. There is no other way. I mean, this is the natural way to do the question. Okay, so now if there are 2 people in 10 places, what should be the answer? right? That's right, 10 into 9. So now if there are two places, two people, M1, okay, so let's just come here, right? M1 and W1 walk into the room. 1 minute. Yeah, M1 and W1 walk into the room and there are 10 places, they see 10 places and this is, they just sit. So they think, oh, okay, we will think about the W1 sitting before M1 later on. They just want to sit first. So then how many ways are there? 10 into 9. Now, if W1 wants to sit before M1, then how many places, how many choices should be there? So you have 10 into 9 ways, many possibilities. But among these, how many possibilities are such that W1 sits before M1? Just half of it, right? That's just the obvious thing, right? Half of it. Obviously, you can just also say that for every arrangement in which W1 sits to the left, you can just swap and you can make an arrangement, right? And so it's just half. Half of it is like that, half of it is in which M1 sits to the left. So it's very simple, right? It is just half of this. So that's a more direct way to get to the same simple thing. Okay. So today we learned about this permitting where we have more places in less people. So with these conditions, this thing, and this is, but you see, this is also 10 choose 2. This is also somehow 10 choose 2. Right? Why is it 10 choose 2? Because you see, it's again very simple. I mean, we see it here as a coincidence, but it's 10 choose 2 simply because it's not a coincidence. It's because, I mean, if you want to seat, so let's pay attention to this again. If you want to seat M1 and W1, so other couples we forget about for the time. We want to seat M1 and W1 in 10 places so that W1 comes before M1. Well, what does that mean? That just means you have to choose 2 places. Is that right? Yeah. If you think about it now from a different perspective, well, if you think about it like this, the way we have done, that's perfectly fine. But if you think about it from a different perspective, right? This just means choosing 2 places. This is the same as choosing 2 places because when you choose 2 places, in the leftmost of the 2 places, in the lefter one to the one in the left position, you place M1. So if you choose 2 places, let's say you chose this and this, that's it. You have to now place W1 here and M1 here. Or if you place some other. So it's just a matter of choosing now. It's just a matter of choosing, no permutations, right? So this is the same as choosing 2 places. That way also you can see it is 10 choose 2. So there are these 2 ways, right, in which you can see the answer is 10 choose 2. Okay, so this is a flavor where you have permutations, but there is some order on the permutations. Then it kind of becomes a combination because once you choose, then there are no arrangements because it is in some relative order is fixed. Okay, right? So now is it clear to everyone the first step? Okay, all right. So these are fundamental things. So this is, we are doing these things, fundamentals here. And then now let's think, what is the next thing to do? So just, yes, right? That's the thing. Now, once you see the idea, then it is very simple. Then now already 2 places are gone, some 2 places, and for any 2 places that are gone, it does not matter which 2 places, for any 2 places that are gone, 8 places are left, and we can choose 2 among them and place W2 and M2. Okay, right? So for example, suppose in the first step you chose these 2 In the first step, you chose these two places and you place W1 and you chose this and this place and you place them. Now 8 places are left and again you choose two. Let's say you choose this place and you choose the last place and you place it. So it does not matter which places you would have chosen first. You would have got 8 to 8, choose two choices for the second place. And this is why this method looks good, because no matter what choice you make in the first step, there are equal number of choices in the second step for every choice in the first step. Okay. So if you continue like this, you will see that you get 10 choose 2, 8 choose 2, 4 choose 2. So somehow the choose 2 makes the problem very, very straightforward. If you don't see this choose 2 thing, then also you can arrive at it as we kind of did and the other ways. But choose, being able to see this permutation problem as, multidimensional choosing in again and again, and the problem just becomes very, very, very nice, very simple. So what is this number? Find a different form for this number. Okay, well, you can already see here. Let's do this one. I'll ask a different related question. 10 factorial, you see 8, what will it be? 8 factorial into 2 factorial, that's 10 choose 2, right? Then you have 8 factorial, 6 factorial, 2 factorial, then 6 choose 2. So you see things are canceling out in a very specific way. And so on. Or let's do it. Last thing is left. 2 choose 2 is just 1, so we are not going to look at it. That's just simple. If you work this out, you get a very interesting quantity. And then you would wonder, could I have not come up with that directly? That we will think next time. There is this, and then there is 2 factorial to the power. What will be the power here? How many times do we have 2 factorial? 5 times, right? Right. So we just placed it here. So in some sense, this is a generalization of choose. When you have a choose, when you have a n choose m a, then what does it become? It becomes n factorial, a factorial, n minus a factorial. Basically, you have a number on the top, it's factorial, and then to the two numbers here whose factorial you're taking, they add up to n. Okay. Here also, these numbers that you're taking factorial of in the denominator, which you're multiplying, they add up to the top one. So it's a kind of a generalization of, so that was a binomial coefficient, if you know that connection. It's called that. You'll see that also very clearly. But just as this choosing was for two things in the denominator which add up to 10, two things in the denominator which add up to 8, and so on. Here you have four things or five things in the denominator, and that, so the number of things in the denominator are increasing, but you're still only multiplying them, and they are adding up to 10. So it is a kind of generalization, right? And we will try to understand these two things and other things under the same umbrella, hopefully soon. Okay, so that will be. So all these things are motivations to explore these things. How do these things arise? Can they arise in algebra also, or do they only arise in counting? Like these things, or can they arise in algebra? Can they arise in geometry? In number of lines, number of intersections, number of. We'll see, and then we will. If let's see what happens. Okay, if they arise or not. So it depends. So there you go. This is the answer. This is the answer. Okay, so it's really about thinking how. So first of all, it's about being clear with the fundamentals that we are clearing up over learning over time, and you are also learning, suppose, and means in the class and on your own and so on. But we are learning the fundamental. That should be, you should be comfortable. It should be like butter, just comfortable with that. Okay. And then comes, how should I place them? Should I first place the woman? Should I first place the man? Or should I do case work? Or should I place the men and women together? Or what? Like, this is the thing that from what angle you should take the problem is can be really game changing. Otherwise, you will get the same answer, but you can get it in a very complicated way. Okay. All right. So now some problems for you guys, because I think we have discussed a few things, and I uh, I don't know if in Brualdi you will find it, because I've already done something contextual. Let's put some problems in this context only, so that we can just attack them just after the class tomorrow. Okay, not after the class, it's already late, but tomorrow and so on, you should do them. So yeah, so number one is show by some, I would prefer combinatorial reasoning, show by some combinatorial reasoning. So this is an idea that I got, the idea of the problem I got from something that Ishana said. What exactly, I will not say. Otherwise, problem will be easy. Combinatorial reasoning, that's the fun. I mean, I am, that's this, it's very enjoyable for me at least, just to pick on these ideas. I mean, obviously I have seen this thing earlier, but how it just naturally comes out is spontaneously from what someone says, and it's an interesting thing, I think. Okay. Show that this is equal to this. Now, obviously, some of you may have seen this already. Some of you know this formula from some progressions. Some of you may have seen this through geometry. You can see this through induction, all kinds of things. But I'm interested in a combinatorial reasoning. Okay, so basically I'm saying that think of a combinatorics problem whose answer is the right hand side. We already did one right now. Obviously this stands for n choose, no, so this is n plus 1. This stands for n plus 1 choose 2. That is certainly true. So that, but you have to think of a problem which, so that you can break it. So my point is that think of a combinatorics problem whose solution is the right hand side, such that that same problem, when you do in a dumb way, maybe in the sense that in a different way, there's no dumb way because it gives you this identity in a different, so that if you do the problem in a different way, then you get the left hand side. Okay, so whenever you do a combinatorics problem in a bad way and there is a good answer, then remember that you are in for an identity. You're in for a very nice equation, because the same answer, once you do it in a bad way and once you do it in a crisp way. Okay, so think about this. Actually, we already saw it in the class, but yes, obviously, yeah. Always, not just this, whatever things I ask you to try and all, not many of you mail me, but I understand sometimes the questions are very vague and you guys have other work, but you have to spend time. Okay. You do 2 classes in the week, 3 classes in the week, but more important is that you spend time. Okay. Because if you're doing these classes, it means that this is your priority, somewhat high in the priority list. Okay. In the sense that, I mean, this is not regular thing. I mean, this is all relative, but so you have to give it time. You have to, yeah. So this is the number one thing. Think about it. If not, just do it in some other way and show. This is the first problem. Okay. Now the second problem is this. Show that, now this is again, we have already done it in some way, but show that 102 factorial. So now these problems are a little going into different directions, which we will explore more of later. 102 factorial divided by 13 factorial, 13 factorial, 13 factorial, 13 factorial, 13 factorial, 37 factorial is an integer. It's not very obvious that this is an integer. Okay, I mean, I mean, it's not directly obvious. And obviously you can't just calculate. So what can you do that you think now? Okay, is an integer. And again, all these problems have multiple solutions, multiple ways you can approach it. So if you can't think of a way that it's done in the class, that's maybe better. just try it. Just do it in some way. Okay, you'll come up with something. And yeah, any questions? Okay. All right. So now the next question is, and this is again related, obviously, is that okay? So four families with 3, 5, okay, 3, 4, 5, 6 members. 3, 4, 5. Okay, maybe I'm starting with 3. Okay, 3, 4, 5, and 6 members, respectively. Whatever, doesn't matter, but respectively. I'm just keeping it simple. Want to sit in. Yeah, Papa. Sorry, one. Such a big rat. She. So we have 11, 15, 18. In 18 places, such that the shortest member of a family sits leftmost. Or maybe I can put it like this. I can put it like this, but it will take more in a sense. Let me put it like this crisply, and then you guys unpack it and do it. Such that for any and for every given family, the members are in ascending order of height from left to right. Ascending order of height from left to right. Okay, what does it mean? It means that the shortest member has to come before the second shortest member, right? And the tallest member has to come in the rightmost position, right? Again, it doesn't mean that they have to come consecutively. Okay, so for example, if this family has A, B, C, D, and the height is the height is like this. Okay, then in my arrangement, A has to come somewhere before B, B has to come somewhere before C, and C has to come somewhere before D. Somewhere before. And this is only for this family. For the other family, they will take care among themselves. They don't care about the members of the other family. Okay, so I'm giving these problems now because I think just to explain the context and to make the questions clear, right? So is the question clear? How we are doing this? Just absolutely. Right. Yeah. So basically, that problem was where we had 5 families, but every family had 2 members, right? And the women had to sit, yeah, and 2 members, 1 man and 1 woman. And so that was a special case of, in some sense, this is a kind of a moving into generalization. This is a question that you can ask yourself also, right? Okay, what if instead of 2 there were 3? Okay, so then the family is the natural analog, right? Yeah, I mean, all these questions we are doing in this family and couple and this, but these are actually, I mean, the way that mathematicians are interested in this, obviously to do this, we use these analogs, and to even solve, we imagine some situations and so on, walk in and so on. But usually these are like, basically we are taking increasing sequences, and or rather I should say, we are taking increasing sequences, and by keeping these increasing sequences as a subsequence of some bigger sequence, we are sort of merging. So we have 4 sequences, one is length 3, one is length 4, one is length 5, one is length 6. And we want to merge these sequences to make a sequence of length 18 in such a way that these sequences remain subsequences, meaning that their relative order does not change. Okay, and all those have a lot of significance to solve problems in other places in mathematics. So whatever your interest is, this, but for us, it's just interesting, I believe, right? Just fun. Yeah. Okay. So these 3 questions. Let me now give more questions. These questions, I suppose, will make you think a bit. Okay. Obviously, you should try from other places also and see. Okay. So you can note it down, or if you have not noted it down. Yeah. Okay. I'll just keep it for a minute. Okay. Yes, I think I will stop today. Okay. So today we didn't go into paths too much, but that's the point. We did other things. I don't understand. There was one other question that I want to ask everybody, but this question was given by Unab. So let me open it and share it with every one of you. And then you guys can also try it. I suppose it's not very difficult, at least the first question. So, okay, meanwhile, I keep this here. Let me open the thing. Okay, yeah. I mean, basically the problem that we solved using the idea of pigeonhole, we also solved it using partial orders. Yeah, right. Otherwise, because pigeonhole principle is not some theorem, it is just yeah. Okay, so I cannot, okay, I can open. Yeah, so let me just open the first image for the time being, and let's just discuss one question only, means that you have to try it first. Let me share that. So I will stop the recording.